Okay, so now let's talk about another kind of wave. So far, all we've been talking about are transverse waves. So what a transverse wave means is that the particles are their displacement. So remember, we'll do the dance. All right, so the wave translates that way. Which way does my elbow, my particle, translate? Up and down, right? So the displacement is perpendicular to the direction of the wave motion. But what if we had something where the displacement was parallel to the wave motion? That might look something like if you have a slinky. Anybody ever play with a slinky? Yes. Yeah. Own it. All right. So if you take a slinky and you give it a little shove, you know how you get that ripple goes and transmits along? They hit each other and they hit into their neighbor. This is what's called longitudinal wave. So longitudinal wave. So the displacement and the wave direction are parallel to one another. Okay. What kind of wave is this? Looks to me like a transverse, because if you can zoom in without getting sick on one little particle here, it looks as though it's going up and down, but sure as heck looks like a little dance, like the wave is actually transmitting that way. Now, check out this one. Ooh. Okay, so here clearly the particles now are oscillating left and right, and that's also a way that this waveform seems to be propagating. Now, one important thing about all the waves we've talked about, the particles themselves are oscillating. They are not traveling at the wave speed. The waveform is something traveling at the speed v. The particles themselves are just oscillating. So here's a slowed down version. I've highlighted a few particles in red, and if you look at their motion, you see that while the crest of the wave, while they travel at some velocity v, the actual particles themselves just bounce back and forth. Okay. So these waves are a little different. So the waves we did last week and earlier today, we're talking about waves on a string, where the string is just bouncing up and down. And we're talking about the amplitude. So here, instead, what we're going to be talking about are pressure waves. So instead of plotting y as a function of x, where y is the amplitude of the string from its rest position, now we're going to be talking about the change in pressure of the system as a function of position. So if you look at this little freeze frame, this is what a wave looks like at one particular time as a function of position. You see that the particles are much more compact here. That means they're going to have a much higher pressure. So if we were to plot the pressure here, it would look like an increase. And then right here, it looks like the particles are much more dilute, so it could be a lower pressure than, say, atmosphere. And so that's going to be a decrease. And this pattern, so we can plot it instead as an amplitude of pressure as a function of position. And that makes it like a little more familiar to the waves that we've been studying so far. So now I should be clear that this pressure is the difference in pressure at a certain position x compared to atmospheric pressure. So all the waves we've been talking about, they're traveling in a medium, okay? And so the medium for these sound waves is they're traveling, for this case, in air. So how fast these things travel, I'm not going to derive this for you. You can go look in the appendices of your textbook, and you can see that the speed of a sound wave goes as the square root of dp d rho. So P here is the pressure, and rho is the density. So let's see if this thing makes sense. First, what's the first thing we should do to see if an equation is even possibly sensible?
Units.
Check the units. Let's do it. All right. Okay, so we have, the velocity of sound, we're told, is dp d rho. So the units of that Okay, what are the units of pressure? Or what is pressure? Force per area, right? So better have the units of force is kilograms, meters per second squared. But it's force per area, so we're going to have over another meters squared, over density, which is mass per volume. So we have kilograms over meters cubed. Okay, so it looks like our kilograms are all going to cancel out. It looks like we have meter here, cancel out with one of those. If we bring this up on top, we're going to have meters cubed over second squared meters. That looks like square root of meters squared second squared, which is meters per second. Ta-da! Yay. So the units match, but does it actually make sense? Okay, so let's look at this equation and think about what that means. So what this is saying is that the speed of the wave is governed by if you change the density of material, how much is the pressure going to change in that material? So let's imagine something where if you change its density by a little bit, and it changes the pressure in that material by a lot. That's a pretty stiff material, right? It's really hard to compress it. So what do you imagine is going to be the speed of sound? Really big, really small? So that means think of it like if there's a lot of pressure from compressing it just a little bit, that's like there's a really strong force constant between everything, right? So that means there's really strong coupling between all the things next to them. So you can imagine that this wave is going to travel really, really fast. So that means essentially all the ways, like I said, we're talking about waves propagating through material. And so the speed of these waves are going to have to do with how stiff the material is and also the inertia of the particles. Let's see how that relates. Oops. So the waves that we do on our rope, we show that the speed of a wave, just like we use right here, is the tension of the rope over its mass density. You can see that there's a kind of a nice relationship. The term on the numerator for both of them is kind of like a force term, and the term in the denominator is kind of like an inertia term. So it seems like this could be a sensible expression for the speed.